Okay. So the density of a gas is like every density. Okay? And to give you a feel for what density is, I'm going to ask a simple question. Which is heavier? A piece of steel or a piece of wood? You automatically want to say steel. But it's not right. Because a redwood is heavier than a paperclip. A piece of wood is heavier than a piece of steel. The beam holding up this building is heavier than a toothpick. Okay? So it's not about what, but that idea. Instinctively, you want to say steel is heavier than wood. It's heavier if they're the same size. If I had the same size piece of wood and piece of steel, the steel would be heavier. And that's the idea of density, how heavy something is for its size. So we compare things that are the same size. And the way you compare things, how heavy they are, and you always compare them at the same size, is you divide. So density is mass divided by volume. How heavy something is divided by how big it was. So it's mass, how heavy, divided by its volume, how big. Now for units, you're going to have the mass will be measured in grams. The volume will be measured in liters. So my units at the end are going to be grams per liter. So in order to find density, I need to know two numbers. I need to know mass, and I need to know volume. Okay? So I'm going to have to get those numbers. Well, it turns out that if you know the formula, just know the formula of the gas, you can figure out its density at STP. Okay. So all I need is the formula. Okay, because from the to find density, I need mass and volume. And density doesn't depend on size. A small piece of wood, big piece of wood have the same density. Because if I make the wood twice as big, it's going to be twice as heavy. And when I do that division, it's going to end up right where I started. So density is independent of size. It's independent of how much you have. If you have twice as much, it'll be twice as heavy. They'll cancel out when you do the division. Half as much, half as heavy, that'll cancel out in the division. So density is independent of size. So it doesn't matter how much I have. So I can pick any amount. And I'm going to pick 1 mole. The reason why I pick 1 mole is because I can figure out how heavy 1 mole is. How heavy 1 mole is called the molar mass, the mass of a mole. Those are the numbers off the periodic table that we add up. And the volume is going to be 22.4 liters because it's a gas at STP. 1 mole is 22.4 liters. So as long as I know the formula, I can figure out how heavy 1 mole is. I divide that by 22.4 liters. That'll tell me how many grams in 22.4 liters, or grams per liter. How dense it is. So let's do a couple examples, and then I want to show you a little impact of that, and talk about, and actually I'll be able to talk about weather. Okay, so find the density of CO2 at STP. So for gases, for us, this whole unit, we're going to be at STP. It's not a room we want to work in. It's 0 degrees Celsius. But we're going to pretend it's that way because it would be easy to recreate. Ice water. So in order to find density, that's mass over volume. I need a mass and I need a volume. If I assume 1 mole then I would have 1 carbon and 2 oxygens. The carbon off the periodic table is 12.01 grams. 2 oxygens, 16 apiece off the periodic table. So 2 times 16 is 32 grams. I add those together and I get 44.01 grams. That's how heavy 1 mole would be. So the mass is 44.01 grams. What's the volume? Well, it's 1 mole. What's the volume of 1 mole of gas? 22.4 liters. Push those buttons. 44.01 divided by 22.4, and you get 1.96. And notice how grams and liters don't cancel out, so I leave them there. Grams over liters, or grams per liter. Extra super tough? Use the numbers you do before. Find the molar mass, divide by the molar volume, you get the density. So let's try it with CH4. Well, we know the volume is going to be 22.4 liters. I can fill that in right away. I just have to find the mass of CH4. That's 1 carbon and 4 hydrogens. For 1 carbon is 12.01 grams off the table. 4 hydrogens off the table would be 4.04 grams. That gives me 16.05 grams as a total. So 16.05 grams is my mass. And I get 0.717. And still grams over liters because those didn't cancel out. Extra super hard? Okay, well, think about the math you do here and answer this question. Which of these gases would have the greatest density? Remember that density is mass over volume, which for us is mass over 22.4 liters. What's going to give me the biggest density? The ones with the biggest mass, right? And you say, ooh, argon's the biggest one on there because argon's 39. No, 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 no. Cl's 35, and there's 2 of them. It's 70.90. So you went to argon as an individual element. Argon's the heaviest, but chlorine doesn't come as an element. We get it in packages of 2. So chlorine would have the highest mass. So when I did division, I get the biggest number. Does that make sense? And that has some impacts. Because anybody know what density decides? What does wood do that steel doesn't? Floats. It floats. Okay? And it floats because it's less dense than water. So if you put a piece of wood in water, the wood, if you figured out how heavy the water would be that took up that much space, the water would be heavier than that wood. So that when the wood, you try to push the wood under the water wants to go under the wood because it's heavier. And eventually lifts the wood out until the amount of water it takes, the amount of water that it's sitting in, that space there, is how much it weighs. It displaces as much water as its weight. Okay? But the fact that density does that leads to some unusual behavior. If I can get this over here. Nope, that's not the one I want. Not the one I previewed. Where'd it go? It's right here. I had it ready to click. Guess we'll go with this one. Okay. We can see what he's doing. Nah, it's going to take too long. We don't have 6 minutes. It's quicker. Okay, so that is a piece of aluminum foil shaped like a boat. It's just floating there, isn't it? It looks like there's some water missing there, doesn't it? If that had been water, that would have made complete sense, right? But there was no water. What the heck's going on there? Well, the answer is it's SF6 gas. SF6, big molar mass, big density. Okay? It's got a big density so that the aluminum boat is floating in it for the same reason it floats in water. The boat has air trapped in it, right? That's what makes the boat float, is the air that's trapped. Because they make boats out of steel. The steel doesn't float, the air inside does. Okay? And the air is less dense than that sulfur hexafluoride, because air is oxygen and nitrogen, 28 grams, 32 grams per mole. SF6, well, that's 150 grams per mole. 5 times as heavy, 5 times as dense. So that the SF6 fills up the bottom of that container, and the boat will float in it just like a boat floats in water, because it pushes the SF6 out of the way, and the SF6 is heavier, just like water's heavier. So that when he reaches down and grabs a cup of the SF6 from the bottom, just like you could grab a cup of water, and pours it in, just like pouring water, replace the air with SF6, it sinks, just like when you replace the air with water in a boat, it sinks. So SF6 has a huge density, so you can float aluminum foil in it. Yeah? That make sense? Because SF6 is going to be a lot heavier than even Cl2. They tell you to get low to the ground during a fire. Okay, that's because oxygen has a lower molar mass than the other pieces. CO2 is heavier. It's going to be higher, and it's one of the reasons. It's bad weather this week, because we have a whole bunch of low pressure systems going over our head. The reason why they're low pressure is because they have water vapor. The water vapor, 18 grams per mole, weighs less than the oxygen and nitrogen. So the stuff over our head weighs less if there's water vapor. So there's less pressure on us. So the reason low pressure is bad weather is because low pressure is due to moisture. It's the water that gives it the low pressure, the dissolved water. Because water is not as dense as oxygen or nitrogen. So the miles of air stacked on top of us don't weigh as much if there's water vapor in it. So that's why low pressure means bad weather. It's because they're bringing moisture to you. Yeah? So what this proves to us is all I need to know is the formula, and I can find its density. Okay? Means I can go the other way. Given the density, we can find out the molar mass of the gas. So they don't know. This is one way of identifying a gas. Is figure out what it's made up of. You don't know what a gas is. You can limit your choices by figuring out how heavy 1 mole is. So the whole secret is pretend you have a mole. Because density doesn't matter how much you have. So if you have a mole, then you can find the mass of a mole, which is the molar mass. So I'm going to take my equation, D equals m over v, and solve it for m. How do I get m up top by itself? Multiply both sides by v, right? So m is d times v. Mass is density times volume. And since we're going to pick 22.4 liters for our volume, since that's 1 mole, the mass I'm going to get is the mass of 1 mole. So let's give this a try. What's the molar mass of a gas with a density of 1.96 grams per liter? 1.964 grams per liter. Well, we said that mass is density times volume. It's the same equation, just solved, right? So the density was 1.964 grams per liter times the volume. Said we're going to use 22.4 liters. So 1.964 times 22.4 equals, my number is 44.0. Unit-wise, the liters on 22.4 liters and the denominator on my density cancel out. And I'm only left with grams, which is really good since I was looking for a mass. I should end up with just grams. If your units work out, you probably set the problem up right. If your units don't work out, you set the problem up wrong. So the liters are going to have to cancel out every time I do this. Because density will always be grams over liters, and the volume will always be liters. So it'll happen every time, if you multiply. If you divide, they don't cancel out. Okay? So what this does me this does me some good. This tells me that this might be carbon dioxide. Because earlier today, our first example, we started off with carbon dioxide. It had a molar mass of 44.01 grams and a density of 1.96 liters, grams per liter. This might be carbon dioxide. I'm not sure because there are other things that weigh near 44 grams. I know it's not carbon monoxide. Carbon monoxide would weigh a lot less than that, right? So you can limit the possibilities of what kind of gas it is. If you do a reaction and separate that gas, by finding its density, you're a step towards identifying it. So you can figure out what unknown stuff you made. Okay? Does that make sense? That's why we'd use this. So, density equals mass over volume, so that mass equals density times volume. So that mass equals 2.86 grams per liter times 22.4 liters. Calculator gives me, I got 64.064, but since I had 3 non-zeros, I picked some 3 non-zeros where I rounded off. You notice I'm not penalizing you for rounding issues. And the units are grams. Extra super tough. Okay, so 64 grams, I know this is not oxygen, because oxygen would be 32 grams. It might be SO2. That's something we figured out weighed about 64. Okay. But I did the math for SF6. The density of SF6 would be 6.52 grams per liter. That's a lot more dense than those other two gases, isn't it? That's why it's sitting at the bottom of that big tank, because it's more dense. And that's why the aluminum can float at it, because it traps enough air to overcome the weight of the aluminum. So, all the things we can change. The central idea of this chapter is the mole. And the first thing we did was we said we could turn numbers, use the periodic table to go between grams and moles. So PT stands for periodic table. Then we learned that we could go between volume and moles. Volume would be liters, right? Volume's liters, mass is grams. And where do I get the numbers for going between volume and moles? Well, you don't get it from someplace. It's always 22.4 liters. We got 1 minute left. Okay. And then mole was really defined based on representative particles. It was the number of carbon atoms in 12 grams of carbon-12. And there we used 6.02 times 10 to the 23rd. But some of our representative particles are made up of smaller pieces. Molecules and formula units are made up of smaller pieces. So if it's a molecule or a formula unit, I can go one more step and turn it into atoms. The homework last night, you took moles, turned it to molecules, and it said molecules, how many atoms there were. The one, actually, it's sitting on the, right? This is the representative particle, and this is a piece of it. It was CHCl3. That was a molecule, okay? And then there were 5 atoms in that molecule. And I got that 5 by counting. If it's a formula unit, I can go to ions as well. And I do that by counting. So, see you Monday. Homework's out of the book. If I don't see you Monday, I'll see you online. We're going to keep moving. Because now we know how to do the math to figure out how much you're going to make when you do a chemical reaction.